Chapter 6 in thermodynamics, the second law. Um, let's talk about the second law of thermodynamics. If you leave a hot coffee out on the counter, you're going to be losing heat to the environment, right? That hot coffee is going to get cold. The cup of hot coffee does not get hotter in a cooler room, right? This is a direction of heat transfer, a direction of energy flow. Same thing with wires. You can run electricity through a wire and generate heat. You can't take heat and put it into a wire and generate electricity. Now, I mean, you could do this in the case of the thermoelectric effect, which is different than this example. So I often get the question about this. Well, what about like thermocouples or thermoelectric heaters or thermoelectric collectors? They work on a different principle. They actually have, they work on the principle of heat flowing from one contact to the other and generate an electric current. That's not a violation of the second law. That's a specific application that has been shown not to violate the second law. But just a regular resistor, right? You can't get a current out of it if you put heat through it. What do we got? Oh, transferring heat to a paddle wheel, right? We often use a diagram of a paddle wheel. We show work used to generate heat, but you can't, you're not going to lift the weight by putting heat on the other side of the paddle. So none of these processes are in violation of the first law. The first law is conservation of energy, right? You could say, oh, okay, well, energy is neither being created or destroyed here. If heat goes from the cool room to the hot coffee, that's still a conservation of energy. But they do violate the second law of thermodynamics. So the second law of thermodynamics basically tells us that processes are going to occur in one direction and not in a reverse direction. So in order for a process to be feasible, it's got to both satisfy the first law, which is conservation of energy, right, and the second law, which is gives you the direction of energy flow from high energy to low. All right, so what is the primary use of the second law? Well, identifying the direction of a process. Will it occur? Research scientists actually, when they're developing new materials or new processes, they might do an analysis to see, okay, is it even possible to make this material, using these synthesis routes, using thermodynamics. And the second law also talks about the quality of energy, right? You can have a certain amount of quantity of energy, but that's the first law, right? It doesn't matter how much quantity of energy you have, as long as it transforms from one form to another. It doesn't talk about the quality of the energy. But the second law talks about what's the quality of energy. So, and a lot of times you'll hear the term quality. We used it for steam. You can also hear quality in terms of heat, right? And typically quality, when it's used in the context of heat, is referring to how high of a temperature it has. And that typically gives us a higher quality in the process, higher temperature, higher quality. So degree of degradation of energy during a process is quality and the second law. And we'll get into more of this stuff as we go through the chapter. And then what's the theoretical limit, right? So you may design something like a refrigeration system or an engine or a power plant, and you want to know, okay, well, how much can we actually get out of this? How much energy or power or work can we get out of this system? And the second law of thermodynamics basically tells you what the theoretical limit is, right? What's the highest efficiency you're going to get? What's the most degree of completion of chemical reactions? So that's in the chemical reaction context. All right, let's talk about thermal energy reservoirs. What is a reservoir? Well, it's a hypothetical body and it has a relatively large thermal capacity, right? So something like a very, very large body of water would be a thermal reservoir. So you could absorb, or the body of water, for example, could absorb a certain amount of heat without a significant change in temperature, right? And that's what a thermal reservoir is. So again, I mentioned lakes, large bodies of water, right? Oceans, lakes, rivers, even the air. You know, the air around us can be used as a thermal reservoir, just because they have a huge amount of mass, and you can dump heat into them, and they don't change by very much, if at all, in temperature. Yeah, so here's examples, right? Atmosphere, river, lake, and for the longest time, people have built factories and such near a river or a lake because they can just pump the water in, use it to cool their process, and dump it back into the lake or the river without a significant effect. All right, a reservoir that supplies energy. Oh yeah, in the form of heat is called a source. So we already talked about, well, we didn't talk about sources, but one that absorbs energy in the form of heat is called a sink. So if it's a very large reservoir and you're using it to supply energy, that's a source. Something like the sun or a furnace. And one that absorbs energy in the form of heat is called a sink, right? So a large body of water, the atmosphere, I don't know, outer space. A reservoir is often called a heat reservoir, right? Because it supplies or absorbs energy in the form of heat. You're typically transferring energy as heat. So this is what you'll typically see in your diagrams. Thermal energy source, right, provides heat. You have some process going on in here, and then you dump heat to a thermal energy sink. So I don't know, think of stuff that think of things that act as thermal sources and sinks.